Okay, next up we have David Schwab from CUNY.
All right. Well, it's a real honor to be here. To temper your expectations a little bit, my talk won't involve anything in the way of deep math per se, but rather I'll be doing more sort of phenomenology in the style of physics, where I'll think about the kinds of phenomena that seem to be exhibited by in this case overparameterized networks, write down a simple model, and try to say something interesting about that simple model. And when I say I in the main part of this talk, I really mean Mingwei, who's a fantastic graduate student at Northwestern. So here's a brief outline of what I'm going to tell you. So I'll start with the sort of phenomenology that I think is important. You've heard most of this already, but I'll just put into your mind the things that I think you should know. I'll take a brief digression on the early phase of training, because most of the phenomenology I'll discuss will be sort of for the later phase. Then I'll tell you about the main results that I have for you. And then at the end, I'll have a bonus section on something completely different. OK. So the central question that I want to think about is something that people have thought about a lot, and it has been discussed in this conference, and that's the generalization gap between training with large batch and with small batches. So just to remind you, while you often get accuracy on the training set that is perfect in both cases, you often see a gap when you try to generalize, where training with small batches outperforms training with large batches. And this is taken from this famous paper. The story that you're often told along with this is, it has two steps. The first is that SGD is supposed to find you minima that are flatter or wider, and that those flatter or wider minima are supposed to be better for generalization, because when you jiggle the loss function from training to test, you'll do less bad when you're in a flatter minimum. So I'm not going to answer this whole question today. What I want to think about mainly is the first half of that argument. So what does SGD do in terms of guiding you to flatter minimum? What does that mean in the context of overparameterized models that people study today? So to go through some of the phenomenology that you need, as we all know now, once you've trained a model, if you look at the Hessian of the loss at the minimum that you found, you often find that the eigenvalues of the Hessian are almost all very close to 0. So before training, you'll find something that looks like this, where you have a large number of large positive eigenvalues, large number of negative eigenvalues. After you've trained, you have a big sea of zeros, and then a small number of these positive eigenvalues. If you zoom in, you see roughly the number of classes for how many sort of non-degenerate directions you have. And you also see that when you train with small batch, the eigenvalues are smaller than they are when you train with large batch.
What is the loss function?
This comes from this paper by Levant Segun. I think this was on MNIST, if I remember right. Oh, the loss function. I believe it's cross entropy. It might be a label smooth.
It will be different from square also.
Yeah. If you look, you also see that there are small negative eigenvalues that remain, and keep that in mind. I'll come back to that later on. But for the most part, the lesson is that you see this big sea of zeros. And in fact, if you zoom into sort of the first steps of training, what you find is that after only 400 iterations, these large negative directions have all but gone away, and you have this huge peak near 0. So this emergence of degeneracy seems to happen very, very early on. OK, so in addition to that, we've heard from, for example, Sanjeev yesterday about connectivity between minima. So if you take two models and you train them up, and you try and do a line interpolation between these two networks, you find that it crosses a region where the performance is terrible. But if you're smart, you can find a path that traverses some valley that allows you to go between these two networks without encountering any loss in performance. There are examples, for example, this recent paper and Sanjeev's work, where you can actually see some of this analytically. There's another experiment along the lines of this that is very recent that I like a lot, from Jonathan Frankel. And here, what he did was he took two networks and he trained them from the same initialization and with the same data order for SGD for a certain number of iterations, and then he let them go with different data orders. And here, this is the number of iterations that you train with the same data order. And what you find is if you pull them apart right from the beginning, and then you do a line interpolation between the resulting networks, the performance goes back up to chance. This is on CFAR 10, I believe. But if you train for around, say, 1 to 2,000 iterations here, now you can actually do just a straight line interpolation between these two networks. So they found not only are they in the same valley, but they're actually in the same sort of like linear valley. So you can do just a line connectivity. This is kind of surprising. Okay, so for our purposes, we're going to do something similar, but we're going to follow the valley along while watching a model train. So first, take a network, train it up. You get your training curves, and the actual network is performing some motion like this. Then what Mingwei did is every so often he took the network and he sent off another training loop where he did large batch, small learning rate training until convergence, and looked at the models along that he found, and if they were line connected, then he was happy. If they weren't line connected, he sampled even more densely along this training path, and then he finds a sort of projected path along what is, if it exists, the bottom of a valley, if not, sort of the closest local minima. And what you find is in the main plot here, where the training and validation losses are plotted, you see that after the first 5 epochs or so, the training loss is essentially 0, while the validation loss is changing significantly. So after the first, around 5 or 10 epochs here, the network seems to be localized in one of these big valleys. And so I want to make the approximation that I want to think about training after this initial phase where you're not squarely in one of these valleys, and imagine that we have a coordinate transformation that we can form such that the loss looks like this, where you have some directions that have some curvature, and that curvature might depend on the other directions that are totally flat. So here you have little n non-zero directions, maybe order a number of classes or so, and then a huge C of 0 directions that nonetheless change the curvature of the model. If I were smart, I would have made the directions that had curvature be hats and the flat ones be bars, but I did it the other way around because I'm not smart. Okay, so this is the sort of phenomenological model I want to think about after a sort of initial phase of training has occurred. But for unrelated reasons, Jonathan, working with myself and Ari while an intern at Facebook, was thinking about the early phase of training and doing a lot of work studying what's happening during the first, say, 2,000 iterations of a ResNet 20. And I'm going to take a brief digression to just tell you some interesting things there. So first of all, we identify within this sort of early phase 3 sort of sub-phases. And for one, you can see if you just look at telemetry of various things like gradient magnitudes, you can see that the gradient magnitudes start extremely high, shoot down, then are a little bit lower for a couple hundred iterations, then stabilize at some value. So you see all these different things happening. Of course, the evaluation accuracy, immediately after a couple hundred iterations is above 50%. Another thing that you see really early on is in the context of what's called the lottery ticket hypothesis. If you don't know what this is, the basic idea is you would like to prune your model, and what you do is you initialize it, you train it up. After it's trained, you prune away the smallest weights, and then you rewind back to the initialization you had, and you keep iterating this. And when you study this on big models, it doesn't work when you rewind back to the initialization. What you have to do is you have to rewind back to a later point during training, and you find that as you prune more, the evaluation accuracy is preserved when you rewind to a later and later point in training up to 2,000 iterations. And then beyond that, you don't get any performance by rewinding to a later point. So say it again?
During training, classification accuracy, you get 100% at some point, and when?
Yeah, essentially you're at 100% for basically all of this.
At what point in this training iteration?
Oh, for over here?
Yeah.
I actually don't remember offhand. Right. So it seems like in the context of this rewinding for the lottery tickets, a lot is happening during these first 2,000 iterations. It is pretty useful for this pruning, and that might change the way you think about lottery tickets, because, as I said, if you're at iteration 2,000, you're getting evaluation accuracy of 70% already. So you might worry that you're putting a lot of information from the data set into this rewinding to 2,000. So we want to think about what do we really need from the data set for this kind of rewinding, and this gives you a sort of quantitative way of studying what the network looks like after a certain number of iterations. So we first tried things like shuffling the weights in different ways amongst layers, amongst filters, preserving signs, all sorts of things. And basically nothing works if you shuffle. So the parameters are highly non-IID at this point. But what was sort of more interesting was we thought about what if we, instead of training on the task for 2,000 iterations, we do a sort of pre-training of a different problem for a certain amount of time. So first we thought, what if we get rid of label information? What if we give random labels? And here I'm showing, again, the sort of gold standard performance is rewinding to 2,000 iterations on the actual task. And if you pre-train with random labels, it just does terribly. You add more epochs of training with random labels. It either does nothing, so you do the same as you did as if you were just starting from the init that you had. But if you pre-train too long, it actually does worse, so you poison yourself. What's interesting is if instead of doing training with random labels, you do a self-supervised rotation task where you rotate the data 90 degrees, 180, and so on, and you ask the model to predict the rotation, and you pre-train on that task for a certain number of epochs. That can work if you pre-train for a while, as good as training on the actual task for 2,000 iterations. You get a similar story, though not quite as well, if you blur the data and do the supervised problem. And it even, but if you put these together, it fails. So this is helping us sort of tease apart, what's going on during this complicated early phase of training, and this sort of pruning framework sort of makes it quantitative. Anyway, so this was just a brief digression. Let me go back to these degenerate valleys that seem to emerge after this early phase, and let me think about SGD when you are in one of these valleys. So to do that, we utilize this beautiful framework by Shoyaida on fluctuation dissipation for SGD. And so if you take the SGD update, you can imagine averaging it over a mini batch. That's what this notation means. And then, of course, you just get the full gradient on average. Show introduces the idea of a stationary state average of some operator defined in this way, and this is the notation for that. And of course, if you're in the stationary state and you have some something that you're measuring, on average, it shouldn't be changing as you are doing mini batch updates. And the other object that's obviously going to be important is the covariance, the non-centered covariance of the gradients averaged over many batches. Okay, so the main thing that I can tell you is that if you're in one of these valleys and you assume that you have a stationary state now just in the non-degenerate space, not in the whole space, but you imagine that the directions of the curvature sort of equilibrate fast, and you also assume that the noise covariance is aligned with the Hessian, then the trace is non-increasing. The trace of the Hessian is non-increasing. So this is the main thing that I can tell you. There are a lot of assumptions that go into this, so I want to check some of those. So to illustrate the first one, so what I mean by a timescale separation or a stationary state in the non-degenerate space looks like this. So if you have some sort of toy loss function here, where you have some directions that have curvature and then the others that just modulate the curvature, you very quickly equilibrate in the directions with curvature, and you get slow motion, almost like aging, that moves you in these degenerate directions that affect the curvature. Okay, so this is what I mean by assuming a stationary state in the non-degenerate directions. Another thing we need to check is it appropriate to assume that the noise covariance is aligned with the Hessian of the loss? A recent paper studied the relationship between various curvature matrices and found that quickly, where quickly is 70,000 gradient steps, the Hessian and the covariance of the noise seem to be highly aligned. We wanted to see whether this happened, even sooner, because 70,000 gradient steps is a fair amount. So Mingwei looked at this in more detail, and he found that after about 10 epochs, just like we were finding as the time scale for sort of descending into one of these valleys, the similarity between the Hessian and the noise covariance seems to be very high. So this seems like a good approximation. So as I promised, no deep math. So the way that you see this is pretty trivial. You just look at how an eigenvalue changes on average during a mini batch update, and then you can import the fluctuation dissipation framework to get the statistics that you need to plug in here. And you can't say anything in particular about what any individual eigenvalue is doing, but if you sum them up, you can clearly see that it's non-increasing. So it's a really simple argument for how this goes. So does this actually work? If we go back to the experiments that I had with these projected paths, and we look at the models that we found along those projected paths, this was the validation loss for the ResNet and the VGG. And here, if you look at the trace at different points on a log scale along this, you see indeed that it's not increasing. Another kind of experiment that you can do is so to take CFAR10, break it up into the training set into half that has real labels, half that has shuffled labels. Train on both, and use that as your initialization. So now you have a model that will get perfect performance on this data set that's sort of half corrupted, and then get rid of the corrupted labels and just keep training on the half that is real labels. And what you find is that, of course, the training loss is 0 the whole time. The validation loss is going down because even though because we basically have gotten rid of the random labels. And as you do this, indeed, the trace also decreases. So going back one slide, I don't want you to go away thinking that I believe that the trace is the right way to predict validation loss. In particular, if you look at these curves here, you see that your best performance was somewhere here, whereas the trace kept decreasing. Okay, so you can really think of this as a sort of entropic force that is pushing the trace to decrease in the following sense. So you could imagine that instead of having a completely degenerate model, you could have some gradients in what were before the degenerate directions. And what you find in that case is that the trace is no longer necessarily monotonic. So you have what you had before, and then you have another term where the trace can be fighting, the trace gradient can be fighting with the actual gradients of the loss. So if you have something like this, where you could keep going down this way, but the curvature is increasing, at some point you'll actually stop. So just to illustrate this, if you take some simple example like this, where the theta 2 direction modulates the curvature in the theta 1 direction, and you do GD, you quickly, for a small value of alpha, get to theta 1 is 0, and then you keep marching down theta 2 into this increasingly sharp valley. If you do SGD instead, you find that theta 2 actually ends up saturating at some value, and you can't go any further. And in this case, you can actually derive analytically what the curve of theta 2 will look like, and it works very well as long as you initialize when you are already in the sort of stationary distribution of theta 1. Okay, so this is what happens when you have SGD noise, but you could ask what happens if you have a general noise structure. And this is thanks to a conversation with Boris. So whenever you have a paper draft, you should send it to Boris, and he'll make it better. So the idea is if you have some function of your spectrum that is sort of monotone in this sense, if instead of using SGD, if you use GD with added noise that has a diagonal covariance of this form, so in the non-degenerate directions, it takes this form, then you can show that this quantity f will be non-increasing under your dynamics. So in particular, maybe you would care about the determinant of the Hessian. So you can choose f to be the log the product of the eigenvalues, and there you find that then you would just need isotropic noise, but again, only in the non-degenerate subspace. So to test this, again, I like toy models, so we constructed a toy model that has the trace and the determinant are anti-correlated with each other, and then added either isotropic or SGD noise. And you see indeed that if you give SGD noise, trace goes down, determinant goes up, and if you add isotropic noise, trace goes up and determinant goes down. So if you know what what it is about the spectrum of the Hessian that you want to control, if it satisfies these monotone properties, you could construct a noise that would steer it in the direction that you want to go. Okay. So everything that I've told you so far relies on assuming that the loss has a bunch of zero directions and no negative directions, no negative eigenvalues of the Hessian. And back in the beginning, I told you that there were negative eigenvalues that people observe. So what's going on there? What I want to argue, and I would love for you to tell me that you disagree with this, that this this simple model that I'm writing down is actually consistent with having negative eigenvalues in the following sense. So if you look at the average value of the loss, in a stationary state, it's going to look something like this, where there's some number c that depends on the batch size and the learning rate and so on. And if you look at the Hessian in the degenerate directions, so you end up with the derivatives of the lambda I, it still is multiplied by the same c here. So if you take a model that is optimized, and then you send off different versions that you re-equilibrate with different learning rates and batch sizes, you should be able to jiggle c up and down, and the average value of the loss should jiggle up and down, and the size of the degenerate Hessian should also be jiggling up and down in a linear way. And indeed, that's what you find if you look at MNIST, that the training loss is perfectly correlated with, in this case, the sum of the negative eigenvalues, which is one way that we could look at the size of this. The sort of take home here is that this form of the loss function that has zero directions with only positive curvature, if that curvature is a function of the degenerate directions, and you're up the walls a little bit, and you're up the walls different amounts, you can generate negative eigenvalues, even though they're not actually there at the bottom. Okay. So are there any questions about this part? Okay, so I'm making good time. So now I want to move on to the second part of my talk, which is some work done by two fantastic postdocs, Kamesh Krishnamurthy and Tankut Kan. Kamesh is a postdoc at Princeton. Tankut is at the Graduate Center, and they're both here and on the market. So you should talk to them and snatch them up before someone else does. So they've recently been looking at developing a theory of gating in recurrent networks. So we've heard a lot about how you can learn a lot by studying infinitely wide feed-forward networks at initialization, and they've been thinking about analogous questions with recurrent networks with gating, using tools like random matrix theory and DMFT. And of course, there's a long history of this kind of work, starting from the seminal work of Sompolinsky and collaborators. But most of the work in this field in the theoretical neuroscience literature is with what are sort of additive models that don't have gates. So you can decorate this basic model by changing the structure of the interaction matrix, by having self-interactions or modular interactions or modular populations and so on. And that gives all sorts of interesting results. But these interactions are still additive. And if you want to train an RNN in machine learning, you're almost surely to be using something with gating, like an LSTM or a GRU. So what Kamesh and Tankut wanted to do was think about what can you say about the dynamics of randomly wired versions of these kinds of guys. And so they started with a continuous time model. So instead of having this additive dynamics, now you add two kinds of gates. There's one gate that sort of dynamically modulates the timescale of each neuron, and one that sort of gates the outputs of each neuron talking to the others. And there's a gain parameter g, and the sigmoids for the gates themselves have a steepness and a location. And for us, the steepness parameter is going to be pretty important. Z undergoes dynamics similar to this, just with a different matrix here. So I didn't write it down here, but so you'd have Z's here, and then it'd be driven by H's. Yeah, so the Z's have a dynamical equation that looks. They have their own dynamical equation that looks like this, but they're driven by the H's. They are not gated themselves, right?
Same J going
Different J's. They'll have their own J's. If you use the DMFT framework, this set of 3n coupled deterministic ODEs gets reduced down to 3 stochastic ODEs. But now the noise that you have has a correlation that needs to be determined self-consistently with the dynamics itself. And they can do this. And what you find is, well, before I say that, the fact that you have a sort of non-trivial noise here is due to the fact that the weights are sort of tied in time. If you imagine unrolling the RNN into a feed-forward network, the weights at every time layer are connected to the previous one. So you end up with this sort of complex, self-consistent problem you need to solve. So they can do that, and you can look at things like the correlation of the neurons and the temporal correlation, and you find that if the coupling matrix if the gating coupling matrix is also IAD random, then theory and simulations agree very well. And if you make the coupling matrix identity, so you have sort of self-gating, then theory and simulations agree at the level of the average, but there's a lot of interesting heterogeneity that remains in the population. From this, you can also compute a phase diagram, and for small values of alpha r, you have a transition between a dynamics where you just have a stable fixed point at 0 and chaos, just like you have in the standard additive model. But as you ramp up alpha r, you get a new regime that emerges where you have a sort of coexistence of chaos and the 0 fixed point. Moreover, when you ramp up the Z gate to be switch-like, you get a whole new regime where you get a bunch of fixed points that are sort of marginally stable that washes out this big regime of chaos. And so you can see this additionally by looking at the maximum Lyapunov exponent, both from the DMFT and from simulations. And if you take horizontal slices of this at different values of alpha r, you see that for small values of alpha r, you get a transition to a positive lambda max at g equals 2. As you ramp up lambda r, you get this interesting behavior where the transition pulls back, and it also becomes discontinuous, where you get a jump from some big negative value to some big positive value. Okay, so that was for this continuous time model. What can you say about these discrete time models, which are the ones that are actually used in machine learning? So let me just tell you a couple of things. So Tankut and Kamesh study the spectrum of the local Jacobian using random matrix theory, and some of the take-home messages that you would find are that the Z and the R gates have sort of distinct behaviors, in the sense that if you ramp up AR from 1 to 10, the main thing that you see is that you get less stable. You get more eigenvalues with real part bigger than 1. On the other hand, if you ramp up AZ, what you find is that you end up getting this sort of clumping behavior near 1, so you get this explosion of very slow directions and long timescales. And you also see this interesting sort of pinching phenomenon where you get this clumping and pinching together. And if you take a slice along the real axis of this density, you can see this very clearly. We get this explosion of eigenvalues really close to real part just less than 1. So this is what happens for the GRU. If you look instead at the LSTM, now you have 3 gates instead of 2, and nonetheless, the story is sort of surprisingly similar in the sense that if you compare column 1 with column 2 and column 3 with column 4, this I gate doesn't really have much of an effect at all, whereas the other two gates tell the same similar story as with the GRU. So of course this is sort of a whirlwind tour of the dynamics of these models, and where we're going with this is looking at what this dynamical perspective can tell you about how to think about different architectural choices and different initialization schemes and whatnot for training, and that work is ongoing. So that's what I wanted to tell you. So let me thank funding, of course, and you for your attention.
Time for questions? Okay, let's thank David.